and aerosols. That's more next later sessions. And this session, we've got several talks related to the stratosphere down to the surface. What I will do is for the invited talks, I guess at about 30 minutes, I'll wave or something and indicate that the 5 minutes or so are left. And for the other talks, probably 12 minutes, I'll indicate the time is just about up. Okay, so first one to welcome Lynn Harvey, who will talk about the role of the polar vortex in whole atmosphere coupling. And I think that's quite an interesting topic because it relates the constituents in the thermosphere all the way down to, I guess, the tropopause, basically. So, okay, so thank you. Go ahead, Lynn. Yeah, I should apologize. I'm over in Europe, so if things blank out, then that's why. But also, I've unfortunately just caught COVID, so I'm a little bit hoarse. So.
Let's see here. All right. Thank you, William, for inviting me to this session. It's my pleasure to speak today about the role of the polar vortex in whole atmosphere coupling. We're going to start off real basic in this talk. I'm going to first remind people why the polar vortex forms and what it looks like today. I'll also talk about very briefly the global residual circulation that results in descent in the vortex. From there, I'll introduce stratospheric, sudden stratospheric warmings and mention that they're linked to variability throughout the atmosphere-ionosphere system. I'll then give an example of how the vortex couples the sun system from the top down via the descent of energetic particle precipitation produced nitrogen oxides. And then I'll give an example of how the vortex couples the atmosphere-ionosphere system from the bottom up via the generation and modulation of gravity waves. So the winter polar vortex, why is it there? It forms in both hemispheres during the wintertime, basically because the Earth is tilted and it's dark, and the polar cap is not receiving any solar illumination. There's no light to for the ozone to absorb, and so this results in an extremely cold polar stratosphere. And due to the thermal wind relation, you get a strong west-east jet stream that encircles the cold air. But it's critical to understand that the vortex is not static. It's constantly moving around, changing shape due to weather systems below and the upward propagation of waves. And this movie was made before we realized that the polar vortex extends well into the mesosphere. So there's a layer above here where the vortex plays a critical role. So what does it look like today? You have to go down to the Antarctic to see the polar vortex. Here we've got a polar stereographic map with the Antarctic continent in the middle. There's the South Pole in the center, and South America's off at 1 o'clock. The colors are wind speed, and the flow is parallel to these lines. So winds blow strong west to east. Today, the Antarctic vortex is slightly shifted off the pole toward the Weddell Sea. It's well-defined and really strong. You can see its dominant center of action in the Southern Hemisphere. And believe it or not, it's still strengthening. It'll get even bigger and stronger. And go to this website, earthnullschool.net. It's pretty cool. You can rotate the globe all over, go look at the flow at all sorts of different altitudes spanning the troposphere and stratosphere and see current conditions. You can also go to the Climate Prediction Center to see what the vortex is doing on any given day in both hemispheres at altitudes throughout the stratosphere up into the lower mesosphere, and also out 2 weeks. So here's the website, and you see down in the Antarctic, very deep, low pressure system, pretty zonally symmetric, but slightly displaced off the pole. The Antarctic vortex is alive and well. You see, as a function of time, here we look at April through December, time series of vortex area, where the envelope shows the range of variability over the last 40 years. This is in the lower stratosphere. The red line is this year. So it's still climbing, it's getting bigger, and it has a couple months yet to reach its maximum in July or August. For a 3D perspective, go to Stratobserve, a cool website hosted by Zach Lawrence. The site remains up to date with current conditions and forecasts, and it shows the 3D structure of the polar vortex. And this is a particularly useful way to look at the polar vortex during stratospheric warming events when the structure can vary wildly with altitude. Today in the Antarctic, the vortex looks much like a funnel where the area broadens with altitude. Defining the vortex in 3D is important to do numerically in order to study it quantitatively. Here's a 3D perspective of the Arctic vortex. The view is of the northern hemisphere from the Pacific Ocean. The vertical axis is altitude. In the stratosphere, the strong westerly polar night jet can be used to define the vortex edge. That's these black layers, the dynamical definition. We now know that the vortex extends well into the mesosphere, and since the wind field can be more complicated and is generally more uncertain at mesospheric altitudes, it's useful to employ a chemical definition, and this works well where there's strong descent, which sets up large tracer gradients at the vortex edge. This is the chemical definition regime. The vortex can even extend up to the mesopause, but this occurs periodically, episodically, and variability due to gravity waves, traveling planetary waves, and tides makes things complicated. Thus, we've been exploring the use of Lagrangian coherent structures or trajectories that define the air parcel history to define when and where the vortex exists at these extremely high altitudes. All right, so I'm going to briefly touch on the mean meridional circulation. The polar vortex is embedded within a rich laboratory of global circulations and atmospheric waves. And this latitude altitude schematic shows that the wave-driven residual circulation results in descent in the polar vortex. There are a variety of gravity waves, tides, and ionospheric processes shown. In addition to convective and orographic gravity waves emanate from jet streams, including the vortex jet. That the vortex is a gravity wave source and modulates gravity waves from lower altitudes results in a bottom-up coupling. Not to introduce sudden stratospheric warmings and mention that they drive variability throughout the entire atmosphere ionosphere system. Here's a map showing a large amplitude planetary wave in the jet stream over North America. Surface weather patterns like this create waves in the jet stream. These waves move toward the east, and they also move up. They propagate upward and they amplify due to decreasing density, and they disturb the polar vortex. Sudden stratospheric warmings are particularly interesting times during which vertical coupling has been a hot topic. They're major disruptions of the polar vortex driven by the upward propagation of planetary waves. Temperature variations are rapid and huge. They can exceed 65 Kelvin or over 150 degrees Fahrenheit. They come in two general flavors, vortex displacement and vortex split events. And the planetary wave forcing is twice as large in the northern hemisphere, resulting in much more disturbed conditions in the stratosphere in the Arctic rather than the Antarctic. And I want to show you an example of a vortex split event from a 3D perspective, actually 4D. So this is the December 2012, January 2013 vortex split event. And it's a 3D rendering of the Arctic vortex colored by temperature. The vertical axis is altitude. You can see it's rather cylindrical shaped to begin with, but then you get these elongations in the stratosphere. That's planetary wave breaking. And in the first week in January, the vortex splits over a deep layer. So two completely separate lobes exist in the stratosphere. Things kind of detach in the mesosphere and recover more quickly due to shorter radiative timescales. The vortex remains split in the stratosphere for a month before fully recovering to its cylindrical shape. And we now know that the effects of these stratospheric warmings are felt through the entire atmosphere-ionosphere system. The schematic presented in Petitella et al. Shows far-reaching connections from the oceans to the ionosphere, and pole to pole, there are a variety of phenomena that respond to stratospheric warmings, from mesospheric cooling to thermospheric warming, a modulation of atmospheric tides, even variations in ocean currents, variations in polar mesospheric clouds over the summer pole, and in the equatorial ionosphere. Thus, stratospheric warmings precondition the ionosphere-thermosphere system to solar and geomagnetic disturbances. All right, moving on to top-down coupling via the descent of energetic particle produced, or EPP, nitrogen oxides, or NOx. The sun bombards Earth's magnetosphere with solar flares, coronal mass ejections, and high-speed streams. Precipitating energetic electrons and solar protons produce hydrogen oxides and nitrogen oxides, which destroy ozone catalytically. The vortex is perfectly situated over the poles where the magnetic field lines converge, and acts to confine the EPP NOx and HOX to high latitudes. Since the HOX is very short-lived, I'm going to hereafter focus on the NOx. Descent in the vortex transports the nitric oxide produced by the ionization down to the stratosphere where the ozone is. Ozone loss due to the descent of EPP-produced NOx is known as the indirect effect, a term coined by Core Randall some 15 years ago. So you have a complicated series of chemical reactions in the thermosphere that produce NOx. That NOx then descends in the polar vortex down to the stratosphere, where the NOx is represented here by the Pac-Man molecule gobbling up the happy ozone molecules. Since ozone is a radiatively active gas, changes to ozone impact the temperature. Changes in temperature gradients change the background winds, which affect the upward propagation of waves. And the polar vortex plays a critical role in all of this coupling. So if you want to learn more about this, I recommend you go to Randall et al. 2015. It provides a great summary of the indirect effect in both observations and modeling. And so they reported that the NOx produced in the model and then that descends into the stratosphere is underestimated. All right, so they use the whole atmosphere community climate model and focus on the year of 2004 as a case study. This version of the model includes auroral electrons and solar proton events, so very low energies and very high energies. It doesn't have medium energy electrons. And the model specifies the dynamics in the troposphere and stratosphere to enable direct comparisons to the model. So what you have here are altitude time sections of 2004 of NOx observed by ACE, FTS, and the model. And you see that the observations indicate that there's much higher NOx that descends down into the stratosphere than what the model shows. The errors, what's causing the discrepancy here has been attributed to either a missing source, like the medium energy electrons, or errors in transport. We're still not sure which is the culprit, but progress has been made. And Josh Pettit wrote a paper last year that included the medium energy source of electrons in the model. And that's what these plots show. Also altitude time sections, also for a year, about 15 years ago. But now in the Southern Hemisphere, where the descent is more it's not as variable. So the transport uncertainties are hopefully smaller. And as you see, the top panels here over the polar cap, 70 to 90 south, shows good agreement between MIPAS observations of NOx and Wacom. However, if you look at the mid latitudes, MIPAS and Wacom are still in disagreement. The model doesn't bring down quite as much NOx at the lower latitudes. So there still is work to be done there. Christine Smith Johnson published this paper just a few months ago that looked at modifying the dynamics and seeing whether or not agreement between the observations and the model improved. They focused on the Southern Hemisphere as well, where the dynamics are less variable, and looked at 2010 as a case study. Here we've got the observations, SOFI observations of NO in black during the year of 2010 at 70 kilometers. And the range of variability is shown in the black. The default Prandtl number in the model is the purple, and decreasing the Prandtl number to 1, which results in more mixing, gives you a better agreement with the SOFI observations. They also looked into decreasing the amplitude of non-orographic gravity waves, and that will result in the gravity waves breaking at a slightly higher altitude and forcing mixing in a region of the atmosphere where it'll bring more NOx down. And this also results in better agreement with the observations. But we have yet to have a study that both uses these improved dynamical parameters and includes the medium energy electrons that Pettit include in the previous study. So that's probably the next step. A paper that I published last year looks at the zonal asymmetries in the descent. So most of the time people average around a latitude circle and look at polar cap averages. And this work really emphasizes that the descent needs to be studied in 3D. We also used the whole atmosphere community climate model, but with thermospheric extension and data assimilation, and explored the role of Lagrangian coherent structures near the mesopause. That's these white regions. They're like eddies in the flow that confine the high NO to high latitudes where photo dissociation doesn't kill it off. And what we found was 5 times stronger descent in planetary wave trough regions, longitudes where there are troughs, versus planetary wave ridges. So you really can't average over the polar cap or around a latitude circle, or you'll obscure what's really going on. Okay, so let's talk about bottom-up coupling via the generation and modulation of gravity waves and their effect on traveling ionospheric disturbances. Gravity waves are ripples in the atmosphere. They're visible in cloud patterns. They're generated by flow over mountains, wind shear, convection, and thunderstorms, hurricanes, any impulse to the flow. They act to redistribute momentum, carrying it from where the waves are generated to where they break. Thus, they act to couple the lower atmosphere to the upper atmosphere and remote regions together. This is a polar map in the Southern Hemisphere. This movie shows the winter of 2016. The colors are gravity wave variance measured by the AIRS instrument. And the thick black band is the edge of the Antarctic vortex based on the MERA-2 reanalysis. Color contours are wind speed. You can see orographic hotspots over the Antarctic Peninsula and the Southern Andes. And the gravity wave vertical wavelength increases in the polar night jet, making the waves visible to the AIRS instrument. This is known as the atmospheric filter. Gravity waves with long vertical wavelengths propagate to higher altitudes. Thus, the vortex acts to modulate waves that enter the thermosphere. The vortex also acts as a source of gravity waves. So overall, you can see that the vortex has an impact on the gravity wave field, and this affects the gravity waves that enter the thermosphere ionosphere from below. In 2016, Nathaniel Frizzell and co-authors focused on winter daytime medium scale traveling ionospheric disturbances observed at high latitudes from 4 high latitude and mid latitude superdarn radars in North America. They concluded that there was no clear correlation between MSTID occurrence at mid latitudes and space weather activity as parameterized by the indices of geomagnetic activity, AE and CMH, the top and middle panels. If you separate the MSTID probability distribution functions, where quiet days are in blue and active days are in red, in the top and middle panels, those two curves look identical. But if you separate the MSTID occurrence, quiet and active, by polar vortex strength indices, you see there's much higher probability of MSTIDs when the polar vortex is strong. The cool thing about this is that, you know, variability in the thermosphere and ionosphere is pretty unpredictable, but we can predict what the vortex is going to do out to about 2 weeks. So knowing what the vortex is going to do and knowing that there's a relationship between TIDs and the vortex provides improved predictability in the thermosphere and ionosphere. So to summarize, the winter vortex is a fast jet stream in the stratosphere and mesosphere encircling a region with confined descent. Planetary wave disturbances result in sudden stratospheric warmings and drive variability throughout the entire atmosphere ionosphere system. I showed an example of top-down coupling where via descent of EPP NOx, the vortex connects auroral altitudes to the stratosphere and affects ozone. And I showed an example of bottom-up coupling where the vortex modulates gravity waves, is a gravity wave source, and is related to traveling ionospheric disturbances. Thank you. I'll take whatever questions people have.
Okay, well, thank you very much. I don't know how best to do that. People can either put their hand up or put something in the chat if they have questions. See if there's a...
Oh, sorry, go ahead.
Yeah, go ahead. Yeah.
Oh, thank you very much for your talk. Very fascinating work. You'll see that I'm also interested in SSWs as the talk to follow, but I was just wondering if, so the one study you're looking at the Southern Hemisphere, and I was just wondering if you've done any comparison in terms of the strength of the gravity waves between the Northern and Southern Hemisphere.
Yeah, we have, there's a project that I'm involved in with Living with a Star, looking at hemispheric asymmetries in the, maybe even magnetosphere. We're pretty much the bottom boundary of this, this team of teams. And this is led by Richard Collins. And we're looking at gravity wave data sets from AIRS and SIPs and VIIRS and so forth. And basically they're twice as many. Gravity waves are 2 times stronger in the Antarctic than the Arctic. You know, you have to be careful because of this atmospheric filter effect, and that it's just that the instruments can only see a certain part of the gravity wave spectrum, and the vortex makes visible because with the high winds, those gravity waves. There could be gravity waves elsewhere that the instruments can't see, and so don't get accounted for, but are still, you know, important to that impart momentum to the flow and so forth. So, but that's kind of the bottom line, is that
Okay.
in the data set that we see, the gravity wave variances are twice as strong in the Antarctic.
Okay, thank you very much.
Sorry, this is did I mute myself? Sorry, just wanted to know what the descent rates are and whether they are different in the two hemispheres.
That's a good question. I think historically we've thought that the descent rates are stronger in the Antarctic. I think the biggest hemispheric difference in the descent is that it's more constant in the Antarctic. You can count on it. Whereas in the Arctic, it could probably be stronger in the wake of some of these prolonged stratospheric warmings where you get an elevated stratopause. But overall, if you average over the winter, because you have more variability in the north, it's not as persistent. And so a seasonal average, the Antarctic is going to win. But if you took, weekly time periods, there are going to be times, I think, that the Arctic would win. But overall, I think that the descent is stronger in the Antarctic.
Okay, and then the I think that at least your paper suggested the descent was stronger in the during I think, was it during a warming or just during a situation where a planetary wave was present? Because there's far less warmings in the southern hemisphere, so whether there's an asymmetry in the NOx penetration downwards as a result of the warmings.
Yeah, so my 2021 paper only focused on the northern hemisphere, and I'm in 2009, so this is one of these prolonged stratospheric warmings with an elevated stratopause, and that's where we found the result that the descent is 5 times stronger in the planetary wave troughs. I've actually extended that study to 15 years, and it's not just a one-off for 2009. It persists in any stratospheric warming. 2013, 2019, 2006, there and other major and minor stratospheric warmings alike that are less impactful. They all show these stronger descent in the trough than the ridge. I have not looked in the southern hemisphere, so that would be a great next step.
Okay. Okay. Are there any other questions? Okay, well, I work in this area as well. I think it's a fascinating area to sort of resolve the fine structure and the broad structure and see how they're all connected. So it's yeah. Anyway, thank you very much for a nice overview and good summary of the talk. So. Okay, so we'll move on to the second speaker, be Kevin Bloxham. He's going to talk about past and predicted temperature trends in the winter Arctic stratosphere and the role of sudden stratospheric warmings. So a related topic to the one that we just had. Okay, so Kevin, so go ahead.
All right, well, thank you very much. And thank you to Dr. Harvey for introducing sudden stratospheric warmings for me. So this is, yeah, a good continuation on of that. So, So my interest in temperature trends, oops, sorry, there we go. My interest in temperature trends really started when I plotted the ERA 5 reanalysis data, looking at the 1980 to 2019 period, and I broke it up according to seasons that you see before you. So you have the winter, spring, summer, and fall. And I mean, in looking at the stratosphere, you see what you would typically expect in the face of climate change, with more anthropogenic emissions of greenhouse gases. Of course, this leads to enhanced cooling, because if you're thinking about long wave radiation, so greenhouse gases in the stratosphere will absorb that long wave radiation, but in turn, they also emit it out to space. And that leads to the overall cooling that we see in each of the seasons in the stratosphere. However, what you may notice is that there is this asymmetry between the winter Arctic stratosphere and the Antarctic stratosphere, in terms of the fact that there's this heating trend that is going on in the Arctic, which does not manifest in the Antarctic. And so I want to understand more about what is going on there. And so you may be wondering, okay, Arctic temperature, what's the big, or sorry, the stratospheric temperature, what's the big deal? Who cares? Maybe one of the more important reasons why this is worth knowing more about is, so in the stratosphere, there is the formation of something called polar stratospheric clouds, and they require really cold temperatures to form, around 196 Kelvin. And it's kind of feared that, so in the face of climate change, and if the stratosphere is going to continue to cool, then PSCs, they may form more in the future. And so what's wrong with that is that polar stratospheric clouds, they allow benign forms of chlorine to attach to them. And so come when the sun starts shining in the spring, and essentially what can happen to that chlorine is that it becomes activated, and this can lead to ozone destruction. And so then if the stratosphere is going to continue to cool, and if polar stratospheric clouds continue, and then there's this ozone destruction, then there may be a delayed recovery to the ozone in the stratosphere. So that's really kind of the reasoning why this is an important topic to look into. And so some of the key components of the research I'll be addressing today. So using ERA 5 reanalysis data in conjunction with a radiative transfer model, RTMG. So this work, which was actually recently published in Climate Dynamics. So I really want to, as I mentioned, understand about the recent temperature trends, but then actually break that down into, okay, well, what are the radiative and dynamical components that are impacting these trends? And then also, when you understand about the trends of the heating rates, you can actually then determine the partial temperature contributions of the heating rates themselves. And so kind of the next step beyond that is then I'm looking into CMIP6 models, and I want to understand how climate models will be able to best replicate the recent temperature trends that we see in the Arctic, and then kind of extrapolate to the future to see if we will continue to see that heating trend that we see. So this is a summary of the partial temperature contributions, which are broken up into radiation, non-radiative parameterized physics, dynamics, the summation of those three. Panel E is the observed temperature trend according to the ERA 5 reanalysis, and then the difference between the two. And so what you can see is that overall, and I mean, this is kind of to be expected, is that radiation has been cooling, and this is predominantly through carbon dioxide that this has occurred. In terms of the non-radiative parameterized physics, so such as latent heating, this is mostly impacting the troposphere. But then dynamics, when we consider dynamics, we are able to kind of recapture that heating feature. And so it appears that the dynamics are indeed leading the temperature trends that we see there. And then in panel G here, this is kind of just summarizing this, these panels where I take the 75 to 90 north average, and then basically just create an atmospheric column, and then you can get a better sense of what is dictating the summation of the partial temperature contributions, that black line. And again, you can kind of see that black dashed line and that black line follow pretty well. and that black dashed line is the dynamics. So now that we've kind of established that dynamics appear to be driving the temperature trends throughout the stratosphere, that's okay, but is there perhaps some underlying process that is ultimately responsible for this? And here we go with the sudden stratospheric warmings. And so I won't go into too much detail about them, but what maybe think about kind of the impact of sudden stratospheric warmings. So for one, so this is the SSW of 2006, and this is looking at the 10 hectopascal layer. And so you can see that you have this large swath of warm air being injected into the stratosphere, where temperature anomalies are approaching 50 Kelvin above normal. So we see that temperature anomalies are definitely a factor. But then also when we look at a Hov-Mueller diagram, so this is the 60 to 90 north average, we can see that as the SSW occurs, you see this downward protrusion of the temperature anomaly towards the tropopause. But then you also see closer to the tropopause that the temperature anomalies can actually last upwards of a couple of months. And again, this is just due to different radiative relaxation timescales. But the fact that the temperature anomalies can last upwards of a couple of months here makes me think that, okay, well, perhaps these SSWs are impacting the temperature trends that we see in the ERA 5 reanalysis data. And so when we go back and we filter the 40-year period according to non-SSW years and then SSW occurring years, and then we do the same partial temperature contributions, we can see that that heating feature has totally disappeared in the non-SSW occurring years. And instead it's widespread cooling throughout the stratosphere, which is consistent with what we would expect in climate change. But instead, when we look at just the SSW occurring years, that heating feature is there, although a stronger magnitude, of course, because we are just considering SSW only those years. So it appears that SSWs are driving the stratospheric temperature trends in the Arctic winter atmosphere over the 1980 to 2019 period, the focus of this portion of the study. And so now that we've seen, okay, so it looks like SSWs are having an impact on the recent temperature trends. Of course, then people want to know, well, what's going to happen in the future? And so in order to understand the future, we really need to understand the past. And so in looking to the future, this is where we turn to CMIP6 models. And so in this portion of the study, so I'm using 24 CMIP6 models, and I'm only considering high top models because in general, they tend to be able to reproduce or capture stratospheric variability a little bit better than low top models. And then we're also just looking at the 1975 to 2014 period, so that is roughly the same as the ERA 5 analysis period as well. And so these are the models that you see here on the right that are part of the study. And so how well do CMIP6 models replicate the recent past? So here we're looking at the temperature trends over that 1975 to 2014 period, broken up according to the fall, winter, and spring. And so you can see in the winter that the composite of those 24 CMIP6 models, it does reproduce a slight heating feature, a positive temperature trends in the lower stratosphere, but it's definitely not as strong as what we saw with the ERA 5 reanalysis. But if you pay attention to the black contours, which are the standard deviation, you can see that it's quite high. And then even among the fall, the standard deviation is quite high as well. And so the reason behind this, so if you just take an example of two of the CMIP6 models, so you can see in this particular one that heating feature is very well captured, but then in other ones that it's just showing widespread cooling throughout the stratosphere. So this is really what's kind of leading to that high degree of variability among the models. And so as we kind of established with our previous work that SSWs appear to be driving the trends. And so what happens then if we filter the 1975 to 2014 period of the CMIP6 model, according to those years with SSWs and those without. So on the top here, this is the years without SSWs. And so we can see that heating feature has disappeared, but again, we see such a large degree of variability. And then here on the bottom is the SSW only years, and then that heating feature is back, but it's not as strong of magnitude as I kind of would have expected. And then again, of course, we have a high degree of variability. And so this is where I kind of have to take pause. And before I go into looking at the future trends, I really need to understand, okay, well, what's going on here, and which models can I kind of trust that are actually replicating the recent trends that we see in the atmosphere. And so we need to kind of understand, okay, well, what's going on with the SSWs that are being detected in these models or being produced in these models. And so in terms of the percent of SSWs per month, if we compare the 24 CMIP6 models on the left here with the era 5, you can see that there is this early season bias among the models, where in the era 5, no SSWs are detected prior to December. And then there are quite a few models that are showing November, October, and then even one in September, so way too early. And then there's also this late season bias where again, they're overproducing the number of SSWs in spring. And then if we're looking at the total SSW frequency and compared to the ERA 5, which is the white dashed line here, and then its standard deviation, the gray, we can see that again, some of the models are overproducing the number of SSWs per year. And so now that we kind of see, okay, there seems to be this biasy, but what could possibly be the underlying reasoning behind this? And so we then turn to the polar vortex itself, because I mean, for an SSW to occur, this requires a disruption of the polar vortex. So the polar vortex needs to be established first before there's an SSW, essentially. And so what we can gather from looking at the formation date, and I should note here that I'm using the zonal winds at 60 degrees north and 10 hectopascal to detect this. So if we look, so at the far right of each of these is the era 5. So for vortex formation, we can see that there is this early season bias among all of the models. So that means that the vortex is forming too soon. And then we look at the breakup date, and again, comparing with ERA 5 here on the right, we can see that a lot of the models are delayed. And so essentially this is saying that the seasonality of the vortex in the models is too long. The vortex is lasting too long. And so this could be what's causing the number of SSWs to be occurring too early or too late. And then even when we look at the vortex strength among the models, so all of the light gray lines here, so those are the climatology of the CMIP6 models, again, looking at 10 hectopascal and 60 north. And the black solid line is the average of all of them. And for references, in the red is the ERA 5 reanalysis climatological vortex strength. And so you can see just how large of variability there is among the vortex strength even. And so then you can then perhaps imagine that, okay, well, if the vortex strength is too weak, then this could mean that the vortex is more easily disrupted and you can get more SSWs to occur. And conversely, if it's too strong, then this may inhibit the formation of SSWs. And so this is another possible reason as to why we are seeing such a large discrepancy. So concluding marks and future work. So we saw with reanalysis that major SSWs are playing a role in the observed temperature trends in the Arctic. These trends are less obvious when we're considering CMIP6 models here. And so really the next steps, and I apologize for not getting into the future aspect of this, but it's going to be, okay, well, which of the CMIP6 models best represent the true state of the atmosphere. And then we're hoping to then extrapolate to the future to see how future trends may change. And will SSWs continue to contribute to these temperature trends in the future as well? So with that, thank you very much. And then here's some eye candy for you. This is an SSW in motion. So with that, I will gladly take any questions you may have.
Okay, well, thank you very much for an interesting talk. Are there any questions? Lynn? I think you have to unmute. Yeah.
I was just clapping, but I can ask a
Oh,
question.
sorry.
So if you had to point to one thing that you would think is responsible for the models falling short, do you think it's, would you blame the gravity waves, or, is it lack, what is it? The model top or the sponge layer, what's going on?
It's hard to say right now. And I mean, I also want to look at the heat fluxes as well and see which one and how it's being forced in that regard. But I mean, just in my analysis so far, I've really only looked at the Vortex kind of the early season and late season biasy. But yeah, it's hard to say right now. I'm just kind of getting into this part of the study, but unfortunately I can't really answer that right now. But I mean, in terms of temperature trends as well, like what I'm also wondering too is among the CMIP6 models is how the radiative relaxation rates are being treated in the models too, because if it's removing too much radiation too quickly, then the temperature anomalies aren't going to persist as long. And so maybe that's why we don't see the heating trends that we may see. And because I've looked at some models where you do see like this increasing frequency of SSWs, but you don't see the temperature trends. And so then of course this is also going to need to diagnose, okay, well, how is the duration of SSWs changing? How is the maximum temperature anomaly of these SSWs changing? And so there's quite a few things to unpack among the CMIP6 models in terms of those parameters, and then kind of disentangle that to see what is really impacting the temperature trends the most.
Thanks.
I guess I have a question. I'm just curious if you have a positive temperature anomaly basically above the tropopause, does that result in enhanced radiative cooling and potentially a mechanism whereby the whereby the atmosphere is cooled?
Yes, I mean, if you have a larger temperature anomaly, this is going to cool, of course, via long wave radiation. But I mean, again, when you have the temperature anomalies in closer to the tropopause, they last longer there because you have more atmosphere to go through, and so I mean that's why that's kind of why we see. That's why I would assume that when we look at these SSW occurring years, that you see the temperature feature closer to the bottom of the stratosphere, because around 10 hectopascals and above, I mean, even though that may be a stronger temperature anomaly there when you have the SSWs, it cools quite quickly. And so I'm kind of assuming then that temperature anomaly won't really show up on the trends because it's just removed too fast, whereas closer to the tropopause, that kind of lingering temperature anomaly associated with the SSW has the chance to remain long enough that it shows up in the trends.
Okay, so it's still in effect in that region, there's still enough, I'm going to use the term blanketing by the CO2, so it doesn't see space in the same way.
Exactly right. Yeah.
Yeah. Okay.
Slightly off topic, but maybe not. Can I ask a question?
Sure.
Of the models you were looking at, the CMAP model, the CMIP models, how many of those, and this is maybe, as I say, off field, are actually interactive and involving chemistry? Because your fundamental element is that this is going to change the ozone layer as a result of the cold or the warm, but how many of them are actually seeing an ozone hole and actually therefore feeding that back onto the temperature?
Unfortunately, I don't have a number off the top of my head. It's only a handful of them.
Okay, but do you think that's important, that interactivity on what's happening in terms of the response?
So I've broken this up before in terms of the partial temperature contributions. So here, this is looking at ozone over that period, and it's actually not as important as I assumed it would have been. A little bit more important over the for this, it was 1980 to 2019 period, but it was actually not as strong compared to CO2. CO2 was the strongest, but again, I mean, it's so reliant again upon SSWs, because I mean, when you have the SSW, you tend to have this large intrusion of ozone into the vortex as well, and so there is the possibility of that impacting long wave cooling as well, but it's not as much going to impact shortwave, because I mean, this occurs during the polar winter, and so it's quite small. I have done a breakdown of the long wave versus shortwave, and I mean, the shortwave is an order of magnitude or less, just because it is winter time. So it's not as important as you might think.
Okay.
Okay. Any other questions? Okay, well, thanks again for an interesting talk. And I think was mentioned earlier, Kent Moore has withdrawn his talk, but to ensure that anybody coming in doesn't sort of miss the talk, we're going to, in effect, adjourn till about 5 past the hour. There's so many different ones, so hopefully everybody knows what I mean by 5 past the hour. And then come back to the next speaker, and yeah, which would be Stephen Bigley. Okay, so anyway, you can. I don't know if anybody has other questions that have come up. We can say it, or we can go on. Okay, so see you in about 50. Oh. Paul Kushner has a question. Okay, Paul, go ahead.
Oh, I'll just ask it through the chat, because I don't even know if Kevin's still here, actually. Is he?
Yep, yeah, I'm still here.
All right, well, I didn't want to keep everybody. So I'll just type it up in the chat. It's going to be more like an offline discussion.
Sure, yeah, that sounds good.
I think, oh, that's good. Somebody else is controlling that. Yeah, so welcome back. So our next speaker is Stephen Bigley, and he's going to talk about assessing Pan-Arctic atmospheric ozone simulation capability within the CMIP air quality modeling system. Okay, so take it away, Stephen.
Okey-doke. Slideshow. Okay. I apologize if you see me looking off to the right. I'm doing this double screen nonsense, so where the camera's in one direction, I'm the other. So as William is saying, this is change in description here. Now we're going right down to the troposphere, actually to the ground, looking at the Arctic atmosphere in terms of its components, in particular ozone simulations. So I will be showing you over the next few minutes some results where we've attempted to look at capacity to model ozone in the Arctic and how well we're doing in terms of that ability. So the abstract is here, and basically I'm highlighted a number of the things I want to target. Namely, we're going to look at capacity. So this is an attempt to, we've run 4 annual simulations using the polar configuration, or the which is quite different from the operational domain. So we're focusing on the Arctic, and so many of the elements are new in that regard, and some elements are actually requiring an enhancement. But we have 4 simulations, which are a series of scenarios around the control to understand how good we're doing. We've chosen the year 2015, and we will be looking at surface ozone measurements throughout the time. The things that came out immediately when we first started analysis was the necessity to examine the biogenic emissions and their impact on the ozone at the surface. So that'll be one of the scenarios, and the other is the role of iodine-mediated ozone deposition. In other words, instead of just having, as many models do, a simple sort of flat rate ozone deposition, we are taking into account using actually one of the SAWA parameterization, which utilizes the fact that the iodine is altering the deposition rate. What impact will that have on the overall simulation? So this is the Pan-Arctic domain. I've just shown you here an ozone for the month of July for 2015. It's just to give you an idea of what we're looking at and where the boundaries are. This is the GEM-MAC system. So that's basically a chemistry model being driven by pilots provided by the GDPS. In other words, the GEM, that's the Canadian forecast model, providing daily pilots running with the same dynamics, the same physics as the GEM, and provided it pumped in with a host of emissions from both anthropogenic, wildfire, and biogenic. And being forced, it's a regional model in terms of the description. So we're having to utilize chemistry boundary conditions, which we utilize the Mozart data set, which you can actually see quite strongly on the simulation here. So what we're going to show you in the next few minutes is effectively the control for 2015, which was actually provided originally as a simulation for the AMAP comparison. And then there'll be 2 experiments I'll show you, the modified biogenic and the sea surface iodine comparisons, to show the impact and how well we're doing. Throughout this analysis, we're looking at as many hourly comparison throughout the year as we could to, and we will look at that regionally, individually, and for the domain to try and understand where the biases are, what processes are possibly being inadequately represented, and then move on ultimately to newer versions with a better representation. What do we mean by the observations that we have? This is a schematic or a map showing you a variety of sources. I've got, in effect, problem number 1, not very many observations, and problem number 2, certain portions of the Pan-Arctic domain are pretty minimal. I won't be talking about the Siberian region because we've just got the one site. Europe and is also, there's a lot more sites, but today I'm going to be concentrating on the 2 regions here, the high Arctic and the northwestern Canada. And that's principally because these are going to give me an idea to examine, number 1, the ocean deposition impact, and number 2, in the northwestern Canada, the boreal forests and the biogenic emissions will give us a signal. So you'll be looking at various sites, which are here, the NAPS, the Canadian NAPS, CAPMON, and the European database EBAS. So I'm going to show you over the next few minutes a series of analyses. These are select sites for the regions in particular. I've highlighted, as I say, high Arctic. So this is simply that's 75 to 90 north, and you've got a series of curves on here. The red is the observational average. It's now for the high Arctic case number, as I've already mentioned, we're right down to only 3 sites. I've actually shown the individual sites here to give you an idea of what that means. So that average is a little bit difficult to interpret because you might have variations and they're lumped together. This is for the winter to spring, so from January through to June, and you can immediately see the observations. The blue is the model. The black is a regional average of the entire domain, because the blue is the model for the specific observational sites only, and I wanted to know how representative I was. And I put on the Mozart data for comparisons as an alternative. That's actually the boundary conditions, but we have it for the domain. What's of interest, of course, and obvious is that the model doesn't have any of the halogen, in other words, bromine chemistry, which generates ozone depletion. And so we're not getting these events, which are pretty clear from the Station Nord site on Spitsbergen, and also the ozone buoy, which is a very powerful data, which I didn't have until recently. So that gives me more. But you can see these events are happening. This is daily data, but they happen fairly regularly on some sites. This is an aspect of the model we knew was absent, and we're actively working on that, and I'll come back to that later, and the newer version of the model will handle that. The statistics here is to indicate and show you that for the entire select region, we're getting around about 4 to 4.5 parts per billion bias, and that's largely because of this inability to simulate the springtime ozone depletion events on the surface of the ice as a result of the bromine chemistry, which is not there. If you look to northwestern Canada, now these are all the control scenarios. I will at the end give you the delta, in other words, the impact from the new parameterizations. But if you look to northwestern Canada, we have, again, same color scheme, a much better representation. The model has a low bias. The blue is hovering below the red curve. We now have far more sites, and these are the individual sites shown on the bottom right. And I've tried to highlight where they are. They're still fairly sparse over the domain, but and again, the regional average, so all points throughout the domain are shown by this black line, and then the shaded area is the interquartile range. The reason I've done that is because I wanted to know how representative was the select sites for the actual full portion of the domain. It's all very well getting it right or wrong compared to the observations, but if it doesn't represent the area that you're considering, it's giving you a misinterpretation, or you're misinterpreting what that means in terms of how you're representing the processes going on throughout that region. One of the things we want to do with the biogenic emissions, of course, is to try and push that blue line closer up towards the red as a result of the fact that the biogenic are actually overdoing the job of emitting isoprene and monoterpenes, and therefore bringing the ozone down to a lower level than it should be. So if we go back to the high Arctic now for the summer and fall, we have, I've done this in a split. Again, the scenario shows in this instance, and we have a problem with observations at the end, so I haven't even bothered plotting them. But in the early portion of the summer in the high Arctic, we're not doing too badly. It's low bias again, so that's where we would be wanting improvement from the ozone deposition in the ocean. But once the beginning of September, or middle of September happens, the model has a seasonal structure which just does not mimic the observations. Even if we have observations out here, but that's something I can talk about maybe if I get time. There's quite a distinct separation in the sites, which would make the average fairly meaningless, because you sort of almost are seeing two regimes. and it's difficult to know which one is the right one. The ozone buoys and the land base in particular have quite distinct signals, so that's a little more difficult to interpret, and we'll come back to that. This is an issue that is as of yet uncharacterized. I need to dig deeper into the model simulation to ask myself, why is the model not mimicking the ozone effective recovery as you go into the fall and the winter? It's still, because of that, of course, the ozone bias is now around about 4 or 5 parts per billion again in that simulation. Northwestern Canada for the summer fall, actually, again, similar to what we saw before, much better simulation. So if you want to feel nice about yourself, and this was, you would realize, obviously the model was generated and built around a sort of an operational forecast for the Canada and North America. So we're now coming back towards the domain where it was originally intended and built for. This simulation is far more reasonable. And again, you can see the blue line is slightly low compared to the red, but is following fairly well in terms of the seasonal structure. But even so, we're talking about 3.5 parts per million bias for that region. So what happens when we do the differencing? Here I've gone to the high Arctic again, and this is showing you the observations all the way to December. So you can see the zigzagging, which is effectively the split observational sites. But if you look to the 3 colored curves, they are effectively the control, the biogenic, and then the oceanographic, ocean deposition enhancement. And there is a small shift. Yes, you're going from the red to the blue, so the ozone iodine mediated deposition is shifting, but nowhere near the amount that it is required to get it towards the observations. And certainly not explain, and I wasn't expecting it to explain the difference in the seasonal non-recovery of the ozone. Strangely enough, it gets close to the lower values in December at the end of the year, but again, I'm not sure what to believe with those observations. And again, this is highlighting, this yellow bars are the shift as a result of the experiment or the upgrade compared to the actual bias, which is there. So when you look on average for that entire period, you're only shifting by about 0.3 of a part per billion, whereas you need to go far bigger impact for that. If you look to the summer and fall, it's a much better signal. Again, the red to the blue is the change that is the enhancement. The black is the observation here. It hasn't, again, done a massive job. It hasn't answered the full bias, but it's certainly moving in the right direction and is more consistent throughout the period, though it does diminish, obviously, with the biogenic emissions petering off as you get into the later in the year. Their influence will be smaller. But again, you can see from the yellow bar here, which is the change as a result of the experiments, that it is a relatively bigger proportion of the main bias, which is present here in the blue and the red. If you look at individual sites, and we have done the individual analysis, you can see a clear line in both cases. So it is going up, and these are the sort of the interquartile range. So even though and these of course have chosen for sites where I knew the impact would be most likely to occur, whereas some of the other sites are going to be not so strongly influenced by the impact.
Okay. 12 minutes, Stephen.
Yep.
Okay.
So here's my summary slide. I hope I timed that right. So I hope what I've tried to say is that the model has an ability, and there are identified initially several variants that were important and have made an impact overall, but don't explain the full low bias that is seen. We know that springtime depletion was a problem and is recognized. And as I say, you may have heard a talk earlier in the CMOS presentation by my colleague Kenjiro Toyota, who is actively building and has built a bromine chemistry representation. That will be going in the very near future when we shift over to yet another version of the GEM-MAX system. The the slow and small ozone recovery seen in the fall is certainly something that needs a lot more analysis. I don't have a characterization of that yet. Need to go into the details of individual sites and expand on that. And obviously, I'm forever fighting the fact that I have too few observational data to compare to. And we will continue progressing. I'd like to thank many people, in particular, all of the observational, because I've gone into the nitty gritty. I've only shown you the line at the end product, be it the modelers in the Air Quality Research Division and the various observational people that have provided the databases that are essential for this sort of comparison. So I'll end it there. Thank you very much.
Okay, thank you. Ozone, again, the subject, but a different level of the atmosphere. Any questions? I guess I've maybe a couple. The variability at the observation sites are the is that real, or is, like, I'm just wondering what the uncertainties are.
Actually, I did have some. I don't know if I did. That's a good question. The main issue, which I have an extra slide if I go down. This, for example, is the observations for that period for the high Arctic. And what you can see here, this is the individual observations. And the ozone buoys are the ones where, so to answer your question, the ozone buoys certainly, I think I need to have a long and hard look as to why they are so distinct from the land-based data, which happens to be the Zeppelin here and the Station Nord. But there are some ozone buoys which are more consistent with the land-based data. But there seems to be, as I say, a sort of a split decision as to what's going on. Now, that may well be also a regional difference. You know, I'm lumping together the entire high Arctic north of 75 North. So I think there's some analysis to be done to find out to what degree this is anomalous in terms of observations or anomalous in terms of trying to put together two processes which are not really representative of the same set of circumstances. Yeah, it might be, but I don't think it is pure and simple that I've got bad data and there's too many of it to say that. I think it's more likely that I'm seeing something which is quite different here, and I need to know whether the model even has any capability of representing it.
Okay, last call. Any other questions? Okay, well, thank you for an interesting talk, and we'll move on to the last speaker of this session. This is Tyler Weisenberg, observations of extreme wildfire VOC enhancements over the Canadian high Arctic. And I'm assume we will find out what VOC is. So,
yeah, I guess I can just start out by saying it stands for volatile organic compounds. Are you able to hear me okay?
Yep.
Okay, perfect. Yep. So I'm Tyler Weisenberg. I'm a student in Kim Strong's group at the University of Toronto. So today, as William mentioned, I'm going to be presenting on my work on observations of extreme wildfire VOC enhancements over the Canadian high Arctic from the 2017 wildfires. So jumping right into a little bit of background. So in 2017, in August, there was two independent and really large-scale wildfires which occurred in British Columbia as well as the Northwest Territories of Canada. The BC fires were actually record-setting in their magnitude and affected a massive area of land. The fire plumes basically merged together from these two fires and then were transported up all the way to the high Arctic, where they led to the largest measured enhancements in ammonia, as well as enhancements in many other biomass burning tracer species. So this was the focus of paper by my predecessor, Eric Lutsch, in 2019. So fires are a pretty significant natural source of VOCs, and competition within these smoke plumes for reactants can basically extend their chemical lifetimes, allowing them to be transported over much larger distances they usually would be able to. So the main species that I look at in this work are peroxyacetyl nitrate, ethylene, methanol, and formic acid. Ethylene, methanol, and formic acid are all directly emitted during biomass burning, and PAN is produced by a secondary formation within the smoke plumes themselves. So recently, we've developed FTIR retrievals for PAN and ethylene and applied them to our solar absorption spectra that we've collected at Pearl in Eureka, Nunavut. So these 2017 fire plume measurements basically provide a really excellent test bed for observations of these species during wildfire conditions. So the main goals of my work here were firstly to expand upon the work that Eric Lutsch did in his 2016 and 2019 papers to encompass these VOC species, PAN, ethylene, methanol, and formic acid. Secondly, I wanted to investigate the trace gas correlations for these aforementioned species during these fires. And lastly, I wanted to compare our observational results with the GeosChem chemical transport model and basically examine the transport of the plume as well. So we have a few different data sets that go into this study, so I figured I'd mention them. So the first, which is our ground-based instrument, so the Pearl FTIR. It's located at the Polar Environment Atmospheric Research Laboratory in Eureka, Nunavut. It's been in operation since July 2006 until present. Although, sorry, it goes up until 2020. We haven't been really able to get any data since COVID hit, but that gives us a really long time series of data to work with already. It's an IFS 125HR high spectral resolution Fourier transform infrared spectrometer produced by Brooker Optics, and it's configured for both near infrared as well as mid infrared measurements. So we use a custom built community solar tracker, which basically follows the sun and directs the solar beam down to the instrument using a series of mirrors. And we make measurements pretty much during clear conditions from polar sunrise in late February to about mid-October or so each year. The data from our instruments contributed to two main measurement networks, so NDAC for our mid-infrared data and TCON for our near-infrared data. And for the mid-infrared data, our retrievals for all the trace gas species are performed using the SFIT4 retrieval software. So to complement our ground-based observations, I also use measurements from the EASI instruments aboard the MET-OP-A and MET-OP-B satellites. And recently, they've been developing artificial neural network retrievals for EASI, known as the ANI retrievals, for a bunch of different VOC species, including PAN, formic acid, methanol. They've also been recently working on a retrieval of ethylene. That one's not yet publicly available, although the EASI team was nice enough to provide that for the purpose of this study. So when I actually do the comparisons with GeosChem, I regrid the EASI data to the model grid, the 2 degree by 2.5 degree model grid. Speaking of GeosChem, I used version 13.3 with full chemistry, so troposphere plus stratosphere. We use MERA2 meteorology, anthropogenic emissions from SEDS, and biogenic emissions from MEGAN. Most importantly, our biomass burning emissions come from the Global Fire Assimilation System, or GFAS, version 1.2. We also tested the Global Fire Emissions Database, or GFED, but it didn't really represent the spatial or temporal pattern of the emissions for these 2017 fires very well compared to observations. So we ran the model at 2 degrees by 2.5 degrees for 2017 with a 1 year spin up of the model leading up to that. So just jumping right into some of the results. So here is an animation I put together of EASI data over the high Arctic region during these August 2017 wildfires. And so from the top left going clockwise, we have methanol, formic acid, acetic acid, CO, ammonia, and PAN. And in particular, I want to draw your attention to the CO and PAN panels because they really show kind of the spatial extent and the magnitude of this enhancement that this wildfire plume caused over the entirety of the high Arctic region. It might be a bit hard to see, but the location of Eureka is marked by a little purple star towards the top of each panel. So now these are measurements from our ground-based instrument located at Eureka, and I plotted all measurements from 2017 in red and all other years in light gray. And you can see that for PAN on the top and ethylene on the bottom, in both cases, we see a really, really extreme jump in the total columns during this mid-August period above the baseline. It's a pretty similar case for methanol and formic acid as well, although the enhancement in methanol is a little bit smaller, but still we see a pretty significant perturbation above the baseline in all of these VOC species. So one other thing that I wanted to look at was the correlations or the trace gas correlations. And usually this is done in relation to a longer lived species like CO. So in this case, CO is plotted on the x-axis and each of the VOC species is plotted on the y-axis. And so the measurements from the fire period itself are plotted in different colors based on the day on which the measurements were made in August. And all other measurements are shown in light gray, I should mention. So in the case of pan and ethylene, we get actually really nice correlations between between ethylene, between each VOC species and CO. And in the case of pan, we get an R of 0.9, and for ethylene, we get R of 0.97. So we get really, really strong correlations between these species. For methanol and formic acid, it's a pretty similar case. We get slightly weaker correlation with methanol, but still relatively good regression. And I should mention that the slopes of these regressions is what we call the enhancement ratios between each species and CO. And again, for formic acid, we get a really nice correlation, R of 0.96. So, since our ground-based FTIR measurements are often made quite far away from the source of these fires, these plumes have undergone some kind of chemical aging, which leads to loss of each species. So we can account for this by computing the emission ratio, which basically is correcting the enhancement ratios for the travel time of the plume, which is about 5 days for these fires, and the lifetimes of each species in the atmosphere. Additionally, on top of that, biomass burning emissions are often characterized by what's known as the emission factor, which is basically defined as the mass of species X, which is emitted per kilogram of dry biomass that's being burned, usually given in units of grams per kilogram. And these emission factors are what's most often reported in the literature. So this allows us to more directly compare with previous studies and previous measurements. So here we calculate the emission factor using that relatively simple equation below, where ER sub X is the calculated emission ratio for each species. EF sub CO is the emission factor of CO, usually taken from the literature, and MW sub X is the molecular weight of species X. And then so to convert our emission ratios that we get in this study, we use the emission factor of CO from the most recent compilation study by André et al. 2019. So I basically compiled all of these into a table for each of the species. So on the top is ethylene, and on the bottom of the table is methanol. And one thing that I want to draw your attention to is from ethylene and our ground-based instrument, we get an emission factor that is significantly larger than many of the previous studies, even larger than IAZI during the same fire period. For methanol, we actually get pretty good agreement between our measurements, both from IAZI and our ground-based instrument and previous studies. Similarly, for formic acid, we get an emission factor, again, that's much larger than previous studies, even compared to IAZI again. Although IAZI on its own during this fire period is, about 2 to 5 times larger than all of the previous emission factors reported in the literature. In the case of pan, we only really calculate the enhancement ratio since it's formed in secondary formation. So, these emission factors that we're seeing, really show the extreme magnitude of this event. And we believe that the differences that we're seeing between our ground-based instrument and IAZI is largely attributed to the lower sensitivity of the IAZI instrument over the Arctic. So moving on to our geochem simulations. So when we ran our first set of simulations using the default settings from GFAS as well as GFED, we basically found that there's a really severe transport error that occurs in the model when comparing with IAZI. And it basically causes the smoke plume to be diverted almost completely around Eureka, which is not what we saw in reality. So we suspect that this issue is really being caused by slower vertical transport in the model, as well as the way the emissions are being injected. So by default, the emissions are basically evenly distributed between the surface in the model and the mean altitude of maximum injection, which is basically calculated using a simple 1D plume rise model. It's basically the midpoint in the smoke plume at the height at which it starts being transported. So here's an animation I included. On the top panel is IAZI A and B data regridded onto the GeoSchem grid. And the middle panel is showing the GeoSchem simulation using this default injection scheme. And just by comparing the two, you can see that IAZI basically sees the plume pass directly over our station in Eureka. But in GeoSchem with this default setting, it basically goes almost completely around Eureka. So one thing that we found is that injecting the emissions at higher altitudes in the model brings the plume transport much more in line with what we see in our observations from both space and from the ground. So, for these British Columbia fires, it's actually the height of the plume is actually quite well constrained, and it's been studied quite a bit in the past, in particular in a paper by Peterson et al. 2018. But the Northwest Territories fires have not really been looked at in the same detail. So to kind of understand what the appropriate injection height for these emissions from the Northwest Territory fires should be, we basically fixed the injection height for the BC fires, and then varied the injection height for the Northwest Territory fires, and then looked at the subsequent enhancement and the correlations with the observations. And basically what we found in the end is that an injection height of 10 kilometers for the Northwest Territory fires and 12.5 kilometers for BC produces the strongest correlations with our observations, both on the ground and as well as with Yazzie. So you can see that I show both the default simulation here in blue, the dotted blue line, as well as the one with our modified injection height scheme in green, as well as the FTIR and Yazzie measurements. And we can see that the one in green agrees a lot more closely with our FTIR measurements. And basically in the default simulation, there's almost no enhancement at Eureka. We do see some differences between Geochem and Yazzie during that peak enhancement around August 18th or so, which again, we think is likely due to the lower sensitivity of Yazzie over the Arctic. But in general, we see very good agreement between Geochem and the FTIR measurements where they're available, particularly on August 19th, 2017. We also see that Geochem is able to capture that small secondary peak on the 21st of August quite well. So one of the last things that I wanted to look into using the model is basically whether we can determine how much secondary formation of these species is actually occurring within the plumes themselves. So to do that, I basically ran an additional set of simulations, switching off the direct emissions from the fires of each individual species, and then looking at what we get, in terms of the subsequent enhancement at Eureka. And you can see that in the case of ethylene and methanol, the top two panels, there's very, very little secondary formation going on. Basically, we don't really see any kind of enhancement at Eureka. Methanol is like a very, very small one, but not much. However, in the case of formic acid, there's still a pretty noticeable enhancement. So, basically from this, we can deduce that the secondary formation is on the order of 18% or so of the peak enhancement. So yeah, to basically conclude, we saw the largest enhancements of these species in our entire 2006 to 2020 Pearl FTIR time series from these August 2017 fires. We calculated the enhancement ratios, emission ratios, and emission factors from both our ground-based instrument and Yazzie during this fire period. And the emission factors that we get for ethylene and formic acid are much, much larger than what's reported in the previous literature. Comparisons between the Pearl FTIR and Yazzie versus the Geochem model near Eureka show pretty severe transport error caused by this injection scheme. However, by modifying the injection scheme and injecting these emissions at a higher altitude, we get a lot stronger agreement with our observations and much stronger correlations as well. Lastly, Geochem sensitivity tests basically show that there's pretty little secondary in plume production of ethylene and methanol, but it is quite a notable component of the formic acid columns that we see at Eureka. So I'm currently actually preparing a paper on this for JGR atmospheres, and I'm happy to take any questions.
Okay, thank you very much for that interesting talk. Any questions? Maybe I can ask one, the differences between, I guess, the Yazzie and the observations at Pearl. To what extent is that an issue of Yazzie sort of averaging over things, or possibly not seeing exactly what's going on versus
Sorry, you're saying?
I think
so the issue with Yazzie, since it's a thermal infrared instrument, is basically over the high latitude regions, you get much lower thermal contrast at the surface, basically a much lower thermal contrast between the surface itself and the air just above it. So it makes it pretty difficult for instruments like Yazi in general to make these kinds of measurements at high latitudes, particularly for these VOC species, because many of them are actually quite difficult retrievals. You know, a lot of them have pretty weak spectral features compared to things like ozone or, you know, CO or methane, for example. So all of this basically combines to make it such that, you know, the sensitivity of these measurements from Yazi are quite a bit lower over these high latitude regions. That's not to say, you know, that they're not still useful. And in particular, these neural network retrievals are actually a pretty large improvement over the old like optimal estimation method approach. But in general, yeah, it's quite difficult for them to make these measurements over the high Arctic. But, you know, during these fires, the fact that there's so much of these species allows them to reliably make these measurements, although maybe with a little bit lower sensitivity than what we have from our ground-based instrument. So
does that mean these have been underestimated in the past?
Yeah, so I mean, it's likely in general. I mean, we've done for some of these species, they've done validation. For formic acid, for example, they've done validation against our ground-based instrument, Eureka, as well as many of the other NDAC instruments. And a lot of the time they find that, you know, at higher latitudes, there's often a low bias in the Yazi versus ground-based instruments, for example. So it is possible. It's likely that there is some kind of underestimation. But outside of, you know, the realm of these fire measurements, you know, these big enhancements, it's even the data from Yazi is even noisier. So it's kind of hard, you know, outside of these fire measurements to make reliable observations from space of these VOCs.
Okay. I think Rachel Chang had a question.
Sure.
I think it seems like we're at the end of time, so
Yep.
I'll save my question for maybe the break or something. Thanks.
Okay.
Yep, no problem.
Okay, sorry, I didn't see you soon enough, Rachel. Okay, thanks.
All right, thank you.
So I guess we have a break and the session begins, what, about half an hour? Sorry, just